students, let's start today's class with the recapitulation of mod 8 counter design, right? The simplest one, you have designed it by yourself, right? In mod 8 counter we require 3 flip-flops, right? Why 3 flip-flop? Because one flip-flop acts as mod 2 counter, so 3 flip-flop will make mod 8 counter, right? For this flip-flop, this particular flip-flop, see J and K are shorted together. Why? Because to we want that this flip-flop should act as a T-type flip-flop, right? And in this case also J1 K1 are shorted, and in this case also J2 K2 are shorted. So we want these flip-flops to act like T-type flip-flops so that they can toggle at their respective clock, at the negative edge of their respective clock. Now these are all negative edge triggered flip-flop. This symbol tells us that. Now this is the clock that is given as input. See, this is the clock that is given as input, and this clock is given from outside, right? Now for this flip-flop, however, the clock is given from Q0, and for this flip-flop the clock is given for Q1. You know that, right? So what would happen when we are applying this clock, right, to this particular flip-flop? The Q0 is going to toggle in each of the negative edge of this clock, right? So this is the clock. So for each of the negative edge, the Q0 is going to toggle, and that is what is happening, right? Q0 is remaining low, and whenever the negative edge comes, it becomes high, and it remains high, and whenever the negative edge comes, it becomes low. It remains low, and whenever the negative edge comes, it becomes high, and this way Q0 changes. What would happen to Q1? Q1 is supposed to toggle at the negative edge of its clock. However, this clock comes from Q0, right? So this clock comes from Q0. Oh God. So this clock comes from Q0, right? So see, this Q1 is going to toggle at the negative edge of Q0. See, it is toggling at the negative edge of Q0, and it is again toggling at the negative edge of Q0, again toggling at negative edge of Q0. So in this way it is changing. And what about Q2? Q2 will be toggling at the negative edge of Q1. You know that, right? So Q2 is toggling at the negative edge of Q1, and again in the negative edge Q2 is toggling. What is the result? The result is, if you start from 0 0 0, the next state becomes 0 0 1, and then it becomes 0 1 0, and then it becomes 0 1 1, and then it becomes 1 0 0, and then it becomes 1 0 1, and in this way, see, we are getting the counting sequence from 0 to 7, right? From n to n minus 1. Understood? So this is mod 8 counter for you. We are today assigning it as up counter. Why up counter? Because it is counting from 0 to 7. So if up counter exists, then you may think that there is an existence of down counter. Yes, it is. Down counters also exist, because we must have seen that during rocket launching or any other launching program, the countdown begins, right? So from 10, then 9, then 8, 7, in this way the countdown goes on, right? So down counters are also required, right? So today we shall learn about these down counters, right? So this is the mod 8 down counter, right? This is mod 8 down counter, right? And what we are seeing, like this up counter, down counter will also require 3 flip-flops, right? What is the change? The clock is given in the first flip-flop, and also J0 K0, J1 K1, J2 K2 all are shorted together to high voltage. What is the change? The change is what we can see here. In case of up counter, we used to give the next clock from Q0, right? And for this flip-flop, the clock was given from Q1. But in this case, the clock is given from Q0 prime, right? And in this case, see, it is given from Q1 prime. However, we are still getting the output for Q0, Q1 and Q2, right? We are still getting the output from Q0, Q1 and Q2 just like before. In this case also, in previous case also, right, when we were giving the positive clocks, this is the up counter, we were getting the output from Q0, Q1, Q2. In this case also, we are getting the output from Q0, Q1, Q2, but here the clock is given from Q0 bar and Q1 bar. Let us see the operation, right? Now this is the clock, right? Let us draw the clock first, right? We have drawn the clock, right? Fine. Now Q0, when will Q0 toggle? When will Q0 toggle? The Q0 will toggle at the negative edge of its own clock, right? So this is the clock. At the negative edge of this clock, Q0 must toggle. So that is what is happening here. Q0 is toggling at the negative edge of the clock, right? So first it is low, when the negative edge comes it becomes high, and the negative edge comes it becomes low, and in this way it is changing, right? Fine. Okay. Now what about Q1? Q1 will be toggling at the negative edge of its own clock, but its own clock is not Q0 anymore. The clock is Q0 prime. So we need to draw Q0 prime first. Q0 prime means what? Q0 prime means just the opposite of Q0. So Q0 we have already drawn, right? So we can draw the opposite of Q0. This is Q1. See, whenever Q0 remains low, Q0 prime becomes high, and when Q0 becomes high, Q0 prime becomes low, and in this way, see, we have drawn Q0 prime, right? So at the negative edges of Q0 prime, what will happen? Q1 is going to toggle. See, Q1 is toggling at the negative edge of Q0 prime. See, it is remaining low, and whenever Q0 prime gets the negative edge, it will toggle, and whenever Q0 prime gives the negative edge, it will toggle. So in this way, Q1 is changing. If you get an insight, what is the negative edge of Q0 prime? Negative edge of Q0 prime is basically positive edge of Q0, isn't it? Because Q0 and Q0 prime just the opposite. So negative edge of Q0 prime will be positive edge of Q0. So actually what we can say, with this change of design, Q1, instead of toggling at the negative edge of Q0, it is toggling at the positive edge of Q0. See, Q1 is toggling at the positive edge of Q0, right? This is the positive edge, rising edge. Q1 is toggling. It is remaining high, high, high. Now whenever the positive edge comes, it is toggling. It is remaining low, 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 and whenever the positive edge comes, it is toggling. So uh, this is this has become this flip flop has become a positive edge triggered flip flop, right? Because we have given Q0 prime as output. What will happen to Q2? Q2 will be toggling at the positive edge of Q1, because we have given the clock input from negative complementary Q1, right? Q1 prime. So Q2 will be toggling at the positive edge of Q1. See, it is toggling at the positive edge of Q1, and again it is toggling at the positive edge of Q1. What is the result, right? We're interested on the result more, right? So what is the result? The result is, see, the first state is 0 0 0, just like before. The first state is 0 0 0. But what about the next state? The next state is 1 1 1, that is 7. Then 1 1 0. Remember, we are drawing output from Q0, Q1 and Q2. We are not drawing output from Q0 bar. So the first state is 0 0 0, the next state is 1 1 1, means 7, then 1 1 0, 6, 1 0 1, 5, 1 0 0, 4, 0 1 1, 3, 2 1 again 0. So it has become a mod 8 down counter. So if you take two flip-flops and connect it in this way, so it will become mod 4 down counter. If you take three flip-flops like this, it will become mod 8 down counter. If you take four flip-flops, it will become mod 16 down counter, right? So now you have learned how to design down counters, right? Now let us try to design up down counter, right, we are trying to design up down counter, right? So this counter should be capable of counting up and down as well, right? Very simple. That is, the design is very simple. We just need a selector circuit. Selector circuit is needed, right? So this is our first J0, K0, Q0. This is the clock. This is J1, K1, Q1, and this is the clock. This is J2, K2, and Q2, and this is the clock, right? Right, fine. Now what we are doing, see the connection. We need T type flip-flops, right? So we are making them T. We are making them T. We are making them T. Now for this is the clock that is given. Now for up counting, Q0 must go to the clock of the next flip-flop, and for up counting, Q1 must go here, right, to the next flip-flop. And for down counting, Q0 prime should go to the clock of next flip-flop and Q1 prime in this case, right? So what we are doing here, we are drawing a selector circuit. The selector circuit will require two AND gates and one OR gate, right? Two AND gates and one OR gate. So see, we are naming this as upline, right? So if upline is 1, then what will happen, that this would be 1, right? See, if upline is 1, then this would be 1, right? This is 1, fine. And whatever may be the Q0, if Q0 is 0, the output will be 0. If Q0 is 1, the output will be 1. So what is happening? Q0 is getting transmitted here, right? Say Q0 is 1, then 1 1 will transmit here, right? Because AND logic is, if all the inputs are 1, the output will be 1, right? So this 1 is coming here. And what about this AND gate? See, a NOT gate is given here, right? So if this upline is 1, this NOT gate will make this 0. So the AND gate output will be 0 no matter what is the other input, right? So this Q0 is getting transmitted here. Q0 prime is not getting. Why? Because the upline is 1, right? Similarly, we need another circuit here, right? This will also be connected to upline, and this is connected to negative upline, right? And we need a OR gate here to give the clock. We need OR gate here, right? So see, this is the circuit. right? So you are either selecting q1 or you are selecting q1 prime, right? So if up is 1, then q0 q1 will be transmitted, and if up is 0, then the NOT gate output will be 1, and as this will remain 1, this will remain 0, then q0 prime q1 prime will be transmitted and it will act as a down counter. So this is a mod 8 mod 8 up down counter, right? Fine. So this is all about asynchronous counters. Now see, these asynchronous counters suffers from some disadvantages also, right? And that is why we need to move from asynchronous counter to synchronous counter. Now these asynchronous counters, whatever we have studied so far is asynchronous counters. Now these asynchronous counters are also named as ripple counter or serial counter, right? So the first drawback of these asynchronous or ripple or serial counter is glitch, 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 right? Now what is glitch? See, if this is the clock, right? This is the clock, the output must toggle at the negative edge of the clock. We have drawn it like this so far, right? This is the clock and the output is toggling. It may be Q0 or Q1, whatever it may be, right? It is toggling just at the negative edge of Q0. This is a theoretical drawing. Why? Because this flip flop is made of what? NAND gates, and these NAND gates are made of transistors. Now transistors operate with currents and voltages, right? So the carriers of the transistors, it may be majority carrier or minority carrier, will require some time to energize themselves. So what is the result? The result is that if you give an input to a transistor gate, you do not get the output readily. Now this is imperceptible because as a human being you cannot distinguish the timing of input and output, but it exists. And as these flip-flops are made of numerous NAND gates, they are actually made of numerous transistors. So all the transistors will have their delay time. So in practice what would happen, Q0, instead of toggling just at the negative edge of the clock, it is subjected to some sort of delay, right? This is the delay, right? Now this delay may also, in the reverse case, may also sustain a particular pulse, right? This is practical. Fine. The this output should have got down to 0, right? This is theoretical. But in practice, what we see that there is a delay, right? Now this delay is referred as, referred as glitch. Why glitch? Because see, if in a timing diagram, we witness delay, right? Like this, if you witness delay, then for a particular state, you cannot tell whether the output was high or the output was low, because it is a combination of both, right? It was low for a certain time and then it became high. So for this t state, you cannot tell what will be the output, it is high or low. So again the output is becoming unpredictable. So these undesired pulse known as glitch, right? This undesired pulse at the output known as glitch. Now what is the massive effect of glitch? Apart from the output getting unpredictable, right, you cannot tell what would be the output, but this is, we are talking about what we are talking about, this is clock and this is q0, but this is not the end. We may have q1, we may have q2, we may have q3. So in this way we may have n number of flip-flops, and this delay will be cumulative. From q0 you are adding only the delay of q0, but from q1 you will add the delay of q0 and q1, and in case of q2 it will be q0, q1 and q2. So this delay gets added up, and what we see that the total propagation delay time becomes n minus 1 into tp, total delay. Total delay is n minus 1 into tp, where n is the number of flip-flop, right, and tp is the propagation delay time, right? So if we talk about mod 4, mod 16, mod 32, only 5 flip-flops are there, or 4 flip-flops or 2 flip-flops. But if you talk about say mod 100, mod 200, in those cases the number of flip-flops will be high, 10, 20 flip-flops are there. So the delay will be cumulative and it will be higher than what we can imagine, right? And with this delay what will happen, the clock will come but it will not show, right? Now this delay can be compared as a clock running slow, right? Slow clock, fast clock, right? So it will become, it will come to us like a delayed clock, right? And that is why clock clock from the output of the previous flip-flop is not the theory that is supported, because always the clock is going to get delayed. Always the clock is going to get delayed. So if we do not want to delay, what should we do? We should give the clock to all the flip-flops simultaneously, or in other words we should give single clock to all the flip-flops, and that single clock to all the flip-flops will give rise to synchronous counter, right? So from the next class we will talk about synchronous counter. Thank you all.